Hello and welcome to Container Bytes. My name is Mofi. I'm a developer relations engineer at Google. In this video, we're going to learn what horizontal pod autoscalers are and how they work in GKE. Let's get started. Let's talk about the purpose of horizontal pod autoscaling. In Kubernetes, we can use the replication controller to control the amount of replicas we have for a given deployment. Using that replication controller, you can increase the number of pod or decrease it whenever necessary. So you could run the command to change the spec replicas count to whatever number, or use the kubectl CLI tool to change the replicas count to whatever number we need. But this is not the behavior we want from an autoscaled system. Imagine you have an application that has very high demand, and you are having to go and manually change this replica count every time there's a spike in traffic, and also go back and scale this down every time the traffic goes away. To control that kind of behavior, that's where horizontal pod autoscaling comes in. Horizontal pod autoscaler can look at metrics of both within the cluster and external to control the replica count of a deployment and scale your deployment up and down whenever necessary. You can scale based on resources like CPU and memory. In this example, we're scaling based on CPU when the average utilization is over 50%. So if you have one pod and that is using 50% of its CPU, horizontal pod autoscaler will spin up a second pod until the average utilization of CPU across all your pods is below 50%. You could also scale based on container resources. This feature has been beta since Kubernetes 1.27. This allows scaling based on utilization on a single container inside a pod. It is very useful for situations where you have multiple containers, like in a sidecar pattern, where you want to scale based on your application and not on the other containers that are in the same pod. This looks very similar to the CPU scaling, but in this example, we're scaling based on CPU usage of container with name application. You can also scale based on custom metrics, which can be of type pods, objects, or external. This feature has been stable since Kubernetes 1.23. Scaling on the pod metrics is averaged across all the pods that are part of the same deployment. This type of scaling only supports type average value. Here in the example, we have type pods where the metric packets per second is being used to scale our deployment. You have to have these metrics available in your Kubernetes cluster to use this type of scaling. The next type of scaling is object metrics. These are different objects from the same namespace. So any object in your Kubernetes namespace that are not pods fall under this category. This supports both value and average value as target type. In this example, we're looking at an ingress object and setting target of value of 2000. So if your ingress is having more than 2000 requests coming in, you're going to scale this deployment. The next type of scaling is based on external metrics. This is anything that is not Kubernetes resources. This can be anything like a PubSub or Google Cloud Storage objects, or anything in between that your Kubernetes cluster knows the metric, and you can scale horizontal pod autoscaling based on that metric. You could also scale based on multiple metrics at the same time. This feature is only available in Autoscaling v2 APIs. This will autoscale to maximum scale recommendation of each metric. In this example, we are scaling based on CPU and the pod metric, and the maximum of 2 value is going to be what horizontal pod autoscaler sets the replica count to. There are a few ways to control the scaling behavior. These are with scaling policies and stabilization window for both scale up and scale down time. For scaling policies, we could set period seconds as the duration the values hold true for. If you have multiple policies set, default is to allow for maximum change. Can be configured to allow minimum change by setting select policy to min. You could also disable a scaling policy to only allow scaling in one direction. In this example, we have a scale down policy where we're setting pods to value of 4 in a period of 60 seconds. We also have a percent of 10% in a period of 60 seconds. Between these two policies, since we only take the maximum value, the second policy will only come into play when you have more than 40 pods. Stabilization window counters replica count instability caused by metrics fluctuation. Imagine a situation where you're scaling based on CPU metrics, and that can change every second. If you have a stabilization window of 300 seconds, autoscaling algorithm will look at that window to find the next desired state. Let's look at an example of horizontal pod autoscaling in a GKE cluster. For the demo, I have a simple Go application. This Go application has only one endpoint called prime. In there, we find all the prime numbers in the first 10,000 integer. We also have a 100 millisecond sleep just to make the request take a little bit longer. And we return with the length of this array. We calculate prime using this function. We build and push this image to artifact registry. Next, we have a deployment with replica count set to 1, and image set to the image we built and pushed. We're giving a resource limit of 128 megabyte RAM and 0.1 CPU. We also create a service with type load balancer. We already have this deployment up and running. kubectl get deploy. We see our instance of 1 ready. We create an instance of horizontal pod autoscaler called instance, which targets our deployment with min replica of 1 and max replica of 100. For metrics, we target CPU and set utilization to 50% average utilization. If we find the public IP of our service with kubectl get service, we can generate some load against this IP address. We run a couple of watch to see when the scaling begins. We generate some load with a load generator. In this case, I'm using Hey to generate 10,000 requests with 50 QPS with 10 concurrent requests every time. At this point, we can see that our HPA CPU usage is at 1%. But after some time of load generation, we should see this number go up. We can see the number has jumped to 99%, so Kubernetes has spun up a second pod to bring that number below 50%. Looks like this load is pretty stable. Let's add a bit more load with another instance of Hey generating 10,000 requests again. With double the load, we can expect our HPA requiring double the amount of pod to handle the requests. As you can see, our target has gone above 50% now, and HPA has spun up another pod to handle the excess request. If the target continues to stay above 50%, HPA will spin up more pods until the target goes below 50%. We can see the fourth pod spin up. We can see our HPA target stabilized at 49% with 4 pods. If we stop generating the load, without any load, we should see the target of our HPA drop down to 1%. And in about 5 minutes, Kubernetes will scale down our deployment back to 1 replica. This is because by default, the stabilization window is set to 5 minutes. This behavior can be controlled by changing that value to any number we want. Usually the default behavior is good enough for most applications. We can see the CPU metric target is at 1%. So after about 5 minutes of the target being below the desired target, HPA will scale our replicas down. As you can see here, after about 5 minutes of inactivity, Kubernetes has scaled down our pod to 1 replica. You can also see that in the HPA here. In this demo, we will see how to scale our deployment using a custom metric from our gateway. I have a cluster here set up with the gateway API enabled, and I'm changing our service to add this annotation that says max rate per endpoint equals to 10. We're switching the service from load balancer to cluster IP because the load balancer will be attached to our gateway instead of our service itself. We then create our gateway resource, and we create the gateway class of GKE L7 GXLB. This creates an L7 global HTTP load balancer. Finally, we create an HTTP route that is going to target our backend of instance. We should be able to get our API endpoint with kubectl get gateway. And we see we get HTTP endpoint here. You also have kubectl get HTTP route, and we see that our instance HTTP route is created. We can get to our application by running curl HTTP the gateway API URL /prime, and we'll see we get the same data as before. We create a new HPA based on this new metric that we can get from our gateway API, which is autoscaling.googleapis.com/gclb-capacity-utilization. If that average value is over 50, we want to scale our deployment from minimum of 1 to maximum of 100. We're running a watch here to show that our HPA is deployed. So is our application with 1 of 1 running. If we generate some load with we will see a number of new replicas show up to handle the additional requests. We get to about 11 replicas or so. We'll stop generating the load here. Because the data continues to come in from our gateway API, we might still scale even after the load generation has stopped. But after about 5 minutes, the replicas will be scaled down just like before. Finally, we can see a more complex example of both CPU metric and this custom object metric being utilized together in a single HPA. Here, we are using our CPU metric of 50% average utilization, as well as our object metric that we just saw. We can also see some additional setting of HPA that we can set here. For example, behavior of scale down, stabilization window seconds set to 30. This is different from the default of 300. In this case, Kubernetes will start scaling down much quicker instead of waiting for whole 5 minutes. We can also set some policies for scale down, like every 15 seconds, get rid of 3 pods maximum, or 10%, whichever is larger. So until we hit 30 pods or more, this policy will be effective. After that, this policy will be effective. We can apply our combined HPA. Now you can see that our target, we have 2 different values that we're looking for. If we keep and watch, we should start seeing pods start to come down as soon as 30 seconds hit. As you can see here, our replica count has started to drop from 17 to 14 because we have that policy of only 3 pod to scale down every 15 seconds. We're going to see that number go from 14 to 11 and slowly go down to 1. We see that we're finally back to 1 running replica. If we generate some load again, we should now see HPA checking both the target to see whichever. If we generate some load again, we should see the HPA targets checking for both the metrics and scaling based on whichever gives the maximum number. We can see here, even though our CPU target is still at 3%, we're spinning up new replicas because our custom metric has crossed its threshold. We'll stop generating the load here. Thank you for joining us for this episode of Container Bytes. If you have any questions or any topic you'd like us to cover, drop us a comment.